Hello, everyone. My name is Sriyash Kakulo, and I welcome you to our IISWC 2020 presentation on our work titled Characterizing the Scale-Up Performance of Microservices Using TeaStore. In our work, we present the first systematic study of microservice performance in a scale-up environment on a state-of-the-art x86 server supporting 128 logical CPUs per socket. This is joint work done with Kanishka Lahiri and KV Subramanian. The key contributions of our work are the following. First, we find that the operating system does poorly in terms of scheduling microservice threads on a modern high core count server. This leads to poor throughput and latency at the application level. Next, we demonstrate significant performance opportunity that exists if the knowledge of the topology of the underlying server is properly exploited. Topology awareness allowed us to get throughput gains of 22% and a mean latency reduction of 18% over a tuned baseline of the application that we studied, that is TeaStore. Finally, via a similarity analysis, we demonstrate that microservices have major differences with respect to spec rate 2017 integer benchmarks, which are typically used to drive processor design today. Attributions are noted at the bottom of the slide. In recent years, cloud-based applications have been evolving from monolithic models to microservices. As seen in the figure on the right, in monolithic model, the entire application is contained in a single binary, while in microservice architecture, the application is broken into a suite of services which communicate with each other. These microservices are typically deployed on a large number of servers. As a result, most research in this field has focused on studying the scheduling and placement of these services in a distributed computing environment. We examine a key orthogonal aspect, that is, how do these applications scale up within a single high core count server? If we plot a graph of the number of cores per socket over the years for mainstream x86 servers, we see an increasing trend with as many as 64 cores per socket available today. This upwards trend has been driven by total cost of ownership advantages that high core count servers offer data center operators today. To accommodate all these cores on one socket, these CPUs are often based on chiplet designs as they deliver good performance scalability at acceptable cost. The figure on the right shows a logical diagram of a single AMD EPYC 7742 processor. The CPU can be viewed as comprising of 4 quadrants, one of which is highlighted at the top of the screen. Each quadrant is in turn broken up into 2 core complex dies, or CCDs. A logical diagram of a CCD is illustrated at the bottom of the screen. Each CCD is broken up into 2 clusters of cores called core complexes, or CCXs. A CCX consists of 4 cores with 2-way simultaneous multithreading and share a 16 MB L3. This gives us a total of 64 cores, 128 logical CPUs, and 256 MB of partitioned L3. It is important to understand how microservices scale in such an environment, and ultimately it's the knowledge of server topology that helps us extract maximum performance from microservices. Coming to the benchmark used in this study, that is TeaStore, it is an open source microservice benchmark based on Java. It emulates an online web store for tea and other related items. TeaStore is broken up into 6 microservices and a MariaDB database. Work is delegated amongst these services, and they are deployed as web services running on Apache Tomcat inside Docker containers. We now come to the chart that is central to the presentation. It illustrates performance scaling versus cores. So we have the throughput on the y-axis and core count on the x-axis for three different configurations: default, scale service, and topology aware. I will talk about how we arrived at these configurations in later slides, but first we take a look at the performance numbers. With an 8x increase in cores going from 8 cores to 64 cores, the default configuration scaled by only 2.9x, while the scale service and topology aware configurations scaled by 5.7x and 7x respectively. These throughput improvements were also accompanied by improvements to the latency of the application. The primary takeaway here is to note that there is significant performance opportunity for microservices when the scaling behavior of the application and the topology of the underlying server CPU is properly exploited. Not doing so leaves a lot of performance on the table. In the rest of the presentation, we'll talk about how we arrived at these two tuned configurations that I just described. The first thing we noticed on running the default configuration is that it does not scale up to high core counts. At 64 cores, we only observed 28% CPU utilization. So clearly, it's not making use of the compute resources available to it. Since microservice applications are a composition of services, it is possible that a service with poor scale-up behavior is bottlenecking the end-to-end application. To verify if this is true, we used a simple iterative algorithm to scale instances of services and identify the most performant configuration. Note that the most performant configuration here is without topology awareness. So we start with one instance of all services as shown on your screen. Let's call this config A. Then we duplicate instances of all services one at a time. So we have config B, config C, and config D. Of the four configurations that I just described, we identify the one with the most performance. So let's assume it's this one. Then we treat this as the new baseline and iterate on top of it, like so. We continue this process till we identify the most performant configuration without topology awareness. Using this simple strategy reveals a large performance space as we see in the figure. On the y-axis, we have the throughput indicated by the blue bars. And we also have the mean latency of each configuration indicated in red. On the x-axis, we have the configuration in terms of the number of instances of recommender, persistence, authentication, and image services. After 5 iterations, we arrived at the most performant configuration, which we refer to as the scaled service configuration, which is a composition of 5 image services with 1 instance of all other services. It's highlighted in orange. So as mentioned earlier, the scaling behavior of microservice applications is only as good as the service with the poorest scaling properties. So a few services may be responsible for bottlenecking the entire application. Quickly going back to the performance scaling chart, we note that understanding the scaling properties of the application allowed us to arrive at the scaled service configuration. In the rest of the talk, we treat the scale service configuration as a tuned baseline and craft a topology-aware configuration on top of it, which gives us further throughput uplifts of 22% and a mean latency reduction of 18%. So to arrive at the topology-aware configuration, we use a methodology which we describe as resource provisioning. It is a two-step process. First, we allocate hardware resources to microservices. This is done based on the requirements of individual services in the baseline run. Secondly, we map the resources to the underlying hardware in a topologically aware manner. The table shows the first step of resource provisioning, that is resource allocation. Based on the average CPU utilization numbers in the baseline run indicated in the second column, we allocate cores to individual microservices as shown in column 3. Similarly, we partition memory using 4 NUMA nodes per socket and allocate these NUMA nodes to microservices. Once allocation is done, the next step is to map these resources to the underlying hardware. To demonstrate the scope of the mapping problem, we set up mapped configuration based on the allocation done in the previous slide. For the purposes of the talk, we will go over 4. The rest are available in the paper. These 4 configurations are illustrated in the figure along with the server topology shown at the top. Recall that a cluster of cores is called a CCX, and 4 CCXs make up a NUMA node since we used 4 NUMA nodes per socket, or NPS4, in these experiments. About configuration 1, we see that the first 7 CCXs are mapped to Web UI service. Since Web UI is mapped across a NUMA node boundary, it has interleaved memory. The next CCX is shared amongst the recommender and the image service. Since describing the configurations from the mapping diagram is difficult, we summarize the characteristics in a table. Column 2 shows the number of CCXs shared by microservices. Column 3 lists the number of microservices with interleaved memory. A high number in any of these 2 columns indicates non-ideal characteristics. Configuration 1, highlighted in green, is the best possible configuration and sees throughput uplifts of 22%. Configuration 2 and 3, highlighted in yellow, have some non-ideal characteristics and see some performance loss compared to configuration 1. Configuration 4, highlighted in red, is particularly bad mapping choice and sees only a performance gain of 1% over baseline. In the next couple of slides, we talk about the problems with default scheduling and how these were overcome by the topology-aware configuration. We start by exploring the problem of interference. The figure shows the CPU utilization heat map for 2 hardware configurations, NPS1 and NPS4. The core numbers are indicated on the y-axis and the microservices are listed on the x-axis. Taking a look at one core cluster or CCX, we note that in both cases, most CCXs are utilized by multiple microservices. This is non-ideal as it results in contention for shared resources in the cache hierarchy. We solve this problem of interference in the topology-aware configuration of the workload, which operates with much stricter affinities. This reduces contention between microservices for shared hardware resources, and it promotes the reuse of code and data within the cache hierarchy. We also measure the rates of software thread migration events experienced by each logical CPU in terms of where the thread migrated to. If the destination is the same CCX, we call it a local migration, which is highlighted in red. If the destination is a remote CCX, we call it a remote migration, and it's highlighted in gray. Remote migrations are more expensive than local migrations and hence need to be controlled. From the figures, we note that NPS1 and NPS4 show similar percentages of local and remote thread migrations. However, in the topology-aware configuration, by restricting services to a set of cores, we were able to eliminate a large portion of these expensive remote thread migrations. We then inspected the benefits of topology awareness in terms of reduction in microarchitectural bottlenecks. The 22% uplift in throughput was driven by similar uplifts in instruction per cycle, or IPC. This IPC gain was primarily coming from 13% fewer LLC misses, 50% reduction in coherence traffic seen at each LLC, and a 60% reduction in instruction TLB miss rates, amongst other stats. Finally, we performed a similarity analysis between TeaStore and other workloads commonly used for evaluating server performance. We analyzed hardware performance counter data spanning a large number of events covering both the CPU core as well as the memory subsystem. We then applied principal component analysis on these events to reduce the dimensionality to 2 for ease of visualization. Figure we observe TeaStore stands out as distinct from a lot of the workhorse workloads like spec rate 2017 integer that drive most design choices. A more directed analysis revealed that front-end stalls and kernel activity are primary differentiators. A more comprehensive analysis is presented in the paper. Attributions are mentioned at the bottom of the slide. To conclude, we demonstrated significant performance opportunity for microservices when the topology of modern chiplet server CPUs are properly exploited. Handcrafting a topology-aware configuration gave us throughput uplifts of as much as 143% over default and 22% over a tuned baseline. The resource provisioning scheme discussed in the talk was for a static load profile. However, in real-world deployments in which application hotspots keep shifting with time, these static schemes do not work. Hence, there is a need to dynamically provision resources. We also found that there are scenarios in which reserving cores for network packet processing is helpful. These considerations and scenarios are discussed in more detail in the paper. The performance opportunity described in this work motivates new research in middleware techniques for management of microservices on high core count server CPUs. Finally, our comparison with microservices with other server workloads shows that they exhibit very different pressure points when compared with spec rate 2017 integer benchmarks, which are used to drive research and development of processor architecture. I will pause for a moment on the disclaimers and attributions slide. That brings us to the end of the talk. Thank you.